December 27th, 2024. A telescope in the Chilean mountains picked up a signal that would soon make headlines across the world. Scientists at the Asteroid Terrestrial Impact Last Alert System, known as ATLAS, spotted something moving fast through space. Not just any space rock drifting through the void, but something on a collision course with our neighborhood. They gave it a name, 2024YR4, and within hours, automated warning systems began calculating its trajectory, its speed, and its potential to hit Earth. The numbers that came back were unsettling. This was not a false alarm. This was real. The asteroid was roughly 50 to 100 meters wide, about the size of a football field or as tall as a 10-story building. To put that in perspective, imagine standing at one end of a sports stadium and looking across to the other side. That entire width, hurtling through space at speeds between 20 and 50 kilometers per second. That kind of size might not sound world-ending, but it carries enough mass and velocity to release devastating kinetic energy. Scientists quickly ran impact simulations. If 2024YR4 were to strike Earth, it would not wipe out human civilization. It would not trigger an ice age or global extinction, but it would absolutely destroy a city. The estimated impact energy ranged between 8 and 10 megatons of TNT. To give you context, that is roughly 500 times more powerful than the atomic bomb dropped on Hiroshima during World War II. It is comparable to some of the largest nuclear tests conducted during the Cold War era. An explosion of that magnitude would vaporize everything within several kilometers of ground zero. The shockwave would flatten buildings, shatter windows dozens of kilometers away, and create a fireball visible from space. And then there is the crater. Scientists estimate that if 2024YR4 hit solid ground, it would carve out a crater 1 to 2 kilometers wide. Think of Arizona's famous meteor crater, the massive hole in the desert left behind by an asteroid impact 50,000 years ago. That crater is about 1.2 kilometers across and over 170 meters deep. 2024YR4 could create something similar, or even larger. Now, here is where things get interesting. Most people hear the word asteroid and immediately think of disaster movies where entire continents are obliterated. But 2024YR4 is not that kind of threat. It sits in a very specific category, dangerous enough to take seriously, but not apocalyptic. It is what scientists call a city destroyer. If it hit a densely populated urban area like New York, Tokyo, or Mumbai, the loss of life would be catastrophic, potentially reaching into the millions depending on the exact impact site. But if it struck the ocean or a remote desert, the damage would be far less severe. A massive splash, a tsunami perhaps, or just another crater in an empty wasteland. Still, the mere fact that this object exists and that it was only discovered in late December 2024 is a wake-up call. Asteroids like this are notoriously hard to detect because they are dark, fast, and small relative to the vastness of space. 2024YR4 spent years orbiting the Sun completely unnoticed until it got close enough for our telescopes to pick it up. By the time Atlas spotted it, astronomers had just over 7 years to figure out whether it would actually hit us. That might sound like a lot of time, but in the world of planetary defense, 7 years is a tight window. The discovery triggered immediate action. Space agencies around the world, including NASA and the European Space Agency, began coordinating observation campaigns. Telescopes on every continent swung into position to track the asteroid's movement. Every new data point helped refine the calculations, narrowing down its exact orbit and trajectory. And as more observations poured in, one thing became clear. This was not going away. 2024YR4 was locked on a path that would bring it extremely close to Earth in 2032. The date was set, December 22nd, 2032. Mark your calendars. That is when this space rock will either pass us by safely or make history as one of the most significant asteroid events in modern times. But here is the twist. Right now, we do not know for sure which outcome will happen. The asteroid is still too far away, and our measurements still have a margin of error. That uncertainty is what makes 2024YR4 so compelling and so concerning. It sits in a grey zone, a probability window where impact is possible but not guaranteed. Early estimates put the chance of collision at around 1 to 2%. That might sound low, like odds you would happily take in a casino. But when the stakes are a city getting wiped off the map, even 1% feels uncomfortably high. And that is why 2024YR4 earned a rare distinction. It was assigned a Level 3 rating on the Torino scale, an international system used to categorize asteroid threats. Most asteroids never make it past Level 0. Level 3 means this object deserves close attention. It means astronomers will continue monitoring it for years. It means governments are taking it seriously. And it means that for the first time in a long time, humanity is facing a credible asteroid threat that we actually have time to prepare for. So what happens next? Scientists will keep watching. Every telescope observation, every radar measurement, every computer simulation brings us closer to the truth. Will 2024YR4 miss us by hundreds of thousands of kilometers, passing harmlessly through space like countless asteroids before it? Or will it thread the needle, slipping through the gravitational keyhole and slamming into Earth with a force of 10 million tons of TNT? The answer is coming, and the world is watching. The world is watching. And the question everyone wants answered is simple. Should we be afraid? When news of 2024YR4 first broke, social media exploded with doomsday predictions and apocalyptic scenarios. But the reality, as is often the case with science, is far more nuanced. Yes, this asteroid is dangerous. But no, it is not going to end the world. Let us break down exactly what kind of threat we are dealing with. First, the raw numbers. Scientists estimate that if 2024YR4 were to strike Earth, it would release energy equivalent to approximately 7.7 to 8 megatons of TNT. To put that in perspective, that is about 500 times more powerful than the atomic bomb dropped on Hiroshima in 1945. It is comparable to the Bighorn nuclear test conducted by the United States on Christmas Island in 1962, one of the largest thermonuclear explosions ever detonated. If you want an even more dramatic comparison, think about the Tunguska event. In 1908, an asteroid roughly the same size as 2024YR4 exploded over a remote region of Siberia. The blast flattened 80 million trees across 2,000 square kilometers of forest. The shockwave was detected thousands of kilometers away. Windows shattered in towns hundreds of kilometers from the impact site. And yet, Because it happened over an uninhabited wilderness, there were no confirmed human casualties. The explosion was so powerful that it knocked people off their feet and shattered windows in villages more than 60 kilometers away. 2024YR4 would deliver a similar punch. But here is the critical thing to understand. Size matters, but so does location. If this asteroid hit a densely populated city, the devastation would be catastrophic. Models suggest that the impact could cause significant damage across an area roughly the size of Washington, D.C. Buildings would be obliterated within the immediate impact zone. Fires would erupt across the region. The shockwave would shatter windows and collapse structures dozens of kilometers away. Depending on where it hit and the population density of the area, casualties could reach into the hundreds of thousands or even millions. But here is the twist. Earth is mostly empty. 70% of our planet is covered by oceans. Of the remaining 30%, much of it is desert, tundra, mountains, and uninhabited wilderness. The odds of 2024YR4 striking a major population center are statistically very low. In fact, the most likely scenario by far is that it would hit somewhere remote. If it splashed down in the Pacific Ocean, the result would be a massive explosion, a localized tsunami perhaps, but minimal casualties. If it slammed into the Sahara Desert or the Australian outback, it would create a spectacular crater and not much else. Just another scar on an already scarred planet. So when you hear that 2024YR4 could destroy a city, that is technically true. But the probability of it actually hitting a city is extremely small. And that brings us to the second critical factor, probability. Early calculations put the chance of impact at around 1 to 2%. But as more observations came in, that number fluctuated wildly. In mid-February 2025, the probability spiked to 3.1%, the highest ever recorded for an asteroid of this size. For a brief moment, astronomers around the world held their breath. Then, as telescopes continued tracking the asteroid, gathering more precise data about its orbit, the probability began to drop. By late February, additional observations effectively ruled out most impact scenarios, and the risk fell to less than 0.36%. Today, as of the most recent calculations, the chance of 2024YR4 hitting Earth stands at an incredibly small fraction of a percent. In other words, right now, there is a 98 to 99% chance of nothing happening. Let that sink in. 98 to 99%. If someone offered you a bet with those odds, you would take it every time. But of course, when the stakes involve the potential destruction of a city and thousands or millions of lives, even a 1% chance feels uncomfortable. And that is why scientists are not taking any chances. They are continuing to monitor the asteroid, refining its trajectory with every new observation. Every telescope measurement narrows down the uncertainty. Every radar ping helps eliminate possible impact paths, and with each passing week the picture becomes clearer. But here is the thing, that small probability is not zero. Not yet. And that is what makes 2024YR4 so fascinating from a scientific standpoint. We are living in a unique moment in human history. For the first time ever, we have the technology to detect an asteroid years in advance, calculate its trajectory with incredible precision, and potentially do something about it if necessary. 100 years ago, we would have had no idea this object was coming. 50 years ago, we might have detected it, but we would have been powerless to respond. Today, we have options, but we will get to that later. For now, let us focus on the immediate question. What exactly happens if this thing hits? Scientists have run detailed simulations based on the asteroid's estimated size, composition, and velocity. The current best estimate is that 2024 YR4 is between 40 and 90 meters in diameter. That might sound like a big range, but it matters enormously. An 80-meter asteroid would impact with 8 times more energy than a 40-meter one. Why? Because when you double the diameter, you increase the volume and mass by a factor of 8. More mass equals more kinetic energy equals a bigger explosion. Based on the asteroid's velocity at atmospheric entry, approximately 17.2 kilometers per second, and its estimated density of around 2,500 kilograms per cubic meter, scientists have determined that 2024 YR4 is most likely a stony asteroid. That is important because stony asteroids behave differently than metallic ones. Instead of slamming into the ground and creating a massive crater, stony asteroids tend to break apart and explode in the atmosphere, creating what is called an airburst. Think Tunguska, think Chelyabinsk. In February 2013, a 20-meter asteroid exploded over Chelyabinsk, Russia, releasing energy equivalent to about 500 kilotons of TNT. The shockwave blew out windows across the city, injured more than 1,500 people, and terrified millions. But it did not kill anyone. 2024 YR4 is roughly 2 to 4 times larger, which means it would release significantly more energy. But the principle is the same. If it explodes in the atmosphere, the damage would spread over a wider area, but with less concentrated destruction than a direct ground impact. Models suggest that an airburst from 2024 YR4 could cause serious damage as far as 50 kilometers from the center of the blast. Windows would shatter, buildings would collapse, fires would ignite, but again the destruction would depend entirely on where it happened. Over a city, catastrophic. Over the ocean, a spectacular show but minimal harm. Over Siberia, another Tunguska, interesting for scientists but largely inconsequential for humanity. So where does that leave us? The bottom line is this: 2024 YR4 is a real threat, but it is not an extinction-level event. It is not going to wipe out human civilization. It is not going to trigger a nuclear winter or mass extinction. At worst, it could destroy a city. At best, it will miss us entirely. And right now, the odds overwhelmingly favor the latter. We are not talking about a coin flip. We are talking about a 98% chance that this asteroid will pass harmlessly by, becoming just another near miss in the cosmic shooting gallery that is our solar system. But that 2%, that small sliver of uncertainty, that is what keeps astronomers up at night, because in the game of planetary defense, even low odds are worth paying attention to. And that is exactly what scientists are doing. Watching, calculating, and preparing for every possible outcome. So far, we have talked about what happens if 2024 YR4 hits, the destruction, the energy, the potential for catastrophic damage. But let us flip the script. What happens if it misses? And more importantly, by how much? Because here is the thing about asteroids. A miss is not just a miss. The distance matters, and in this case, the numbers tell a story that is equal parts fascinating and reassuring. If 2024YR4 stays on its most likely trajectory, the current models predict that it will pass Earth at a distance roughly equivalent to the Earth-Moon distance. That is approximately 380,000 kilometers away. To put that in perspective, that is far enough that you could fit 30 Earths side by side between us and the asteroid. That is not a close call. That is a comfortable margin. That is a distance so large that amateur astronomers with backyard telescopes could track it safely as it drifts past. In fact, if 2024YR4 does pass at that distance, it would become one of the most anticipated astronomical events of the decade. Observatories around the world would turn their instruments toward the sky. Live streams would broadcast the pass in real time. Schools would organize viewing parties. It would be a moment of collective relief and scientific celebration. A reminder that we live in a cosmic shooting gallery, but also that we are getting pretty good at dodging the bullets. But here is where things get even more interesting. While the most likely scenario is a safe flyby, there is still a narrow range of uncertainty. That uncertainty creates what scientists call an impact corridor. Imagine a line drawn across the surface of Earth. If 2024YR4 were to hit, it would have to strike somewhere along that line. And thanks to detailed orbital calculations, we know exactly where that line is. The impact corridor for 2024YR4 stretches across some of the most densely populated and geographically significant regions on the planet. It begins in the Pacific Ocean, sweeping eastward across the open water before crossing into northern South America. From there, it continues across the Atlantic Ocean, cuts through North Africa, passes over the Arabian Peninsula, crosses the Arabian Sea, and then slices through India before finally extending into Southeast Asia. That corridor represents the only possible impact zones. Anywhere else on Earth is completely safe, but within that corridor, the stakes are high. Cities like Lima, Bogota, Lagos, Cairo, Mumbai, and Bangkok all sit within the potential impact path. If the asteroid were to hit anywhere along that line, the consequences would depend entirely on the exact location. A strike in the Pacific or Atlantic would be dramatic, but largely harmless. A strike in North Africa or India could be catastrophic. But again, and this cannot be stressed enough, the odds of any impact at all are currently less than 1%. The most likely outcome by an overwhelming margin is that 2024YR4 will pass harmlessly by. And when it does, scientists will breathe a collective sigh of relief. But they will not stop watching. Because here is the reality of asteroid tracking. Even a miss today does not guarantee safety forever. Asteroids orbit the Sun. They come back around. And every time they pass near Earth, our planet's gravity tugs on them, altering their trajectory ever so slightly. This phenomenon is called a gravitational keyhole. Imagine a tiny window in space, just a few hundred meters wide. If an asteroid passes through that keyhole, Earth's gravity will bend its orbit just enough to send it on a collision course during its next pass. It is like threading a needle, except the needle is moving at tens of thousands of kilometers per hour, and the thread is a space rock the size of a city block. For 2024YR4, the 2032 pass is not the end of the story. Even if it misses us in December 2032, astronomers will continue tracking it to see if it passes through a gravitational keyhole that could set up a future impact. That is why every observation matters. Every data point helps narrow down the trajectory. Every telescope measurement reduces the uncertainty, and with each passing month the picture becomes clearer. But let us assume the best-case scenario. Let us assume that 2024YR4 passes at a safe distance, well outside the impact corridor, and continues on its way through the solar system. What then? Well, for one, it would mark a major milestone in planetary defense. It would prove that our detection systems work, that we can spot potentially hazardous asteroids years in advance, that we can calculate their orbits with incredible precision, and that we can communicate the risk to the public in a way that is both accurate and reassuring. It would also serve as a wake-up call, because 2024YR4 is not unique. There are thousands of asteroids out there, many of which we have not yet discovered. Some of them are on trajectories that could bring them dangerously close to Earth. And unlike 2024YR4, we might not have 7 years of warning. We might have months or weeks, or in the worst-case scenario, just days. That is why astronomers around the world are working tirelessly to catalogue every near-Earth object larger than 140 meters. That is the size threshold at which an asteroid becomes a regional threat. Anything smaller, like 2024YR4, can still cause significant damage, but it will not end civilization. Anything larger, and the stakes go up exponentially. So what does a safe pass look like from a scientific perspective? First, it means that telescopes will continue tracking the asteroid right up until the moment it passes by. Ground-based observatories in Chile, Hawaii, Arizona, and Spain will all be watching. Space-based telescopes, including those operated by NASA and the European Space Agency, will also be monitoring the pass. Radar systems will ping the asteroid, measuring its distance and velocity with incredible accuracy. And all of that data will be fed into computer models that simulate the asteroid's orbit for decades into the future. Second, it means that planetary defense agencies will use 2024YR4 as a test case. They will run simulations to see how quickly they could respond if the trajectory changed. They will evaluate communication strategies to ensure that accurate information reaches the public. They will coordinate with international partners to make sure everyone is on the same page. In many ways, 2024YR4 is a dress rehearsal, a chance to test our systems, refine our protocols, and identify weaknesses before the real thing comes along. Third, it means that the public will get a front-row seat to one of the most significant near-miss events in modern history. When 2024YR4 passes by in December 2032, it will be visible to telescopes around the world. Astronomers will share images and videos online. News outlets will cover the event live, and for a brief moment, humanity will collectively look up at the sky and appreciate just how fragile our existence is. But here is the thing. Even if 2024YR4 misses, the threat does not go away. Asteroids are not a one-time problem. They are an ongoing challenge. Every year, Earth is bombarded by thousands of tons of space debris. Most of it burns up in the atmosphere, creating the meteor showers we see on clear nights. But every few decades, something bigger gets through. Something like Tunguska, something like Chelyabinsk, and eventually something like 2024YR4. The question is not if another asteroid will threaten Earth. The question is when. and whether we will be ready. That is why 2024YR4 matters, not because it is going to hit us, the odds say it will not, but because it forces us to confront the reality that we live on a tiny blue marble in a chaotic, violent universe. A universe where space rocks the size of football fields are constantly zipping past us at tens of thousands of kilometers per hour. A universe where a small gravitational nudge or an unlucky trajectory could send one of those rocks straight toward us. 2024YR4 is a reminder that we are not invincible, that the sky above us is not empty, that the universe does not care about our cities, our civilizations, our hopes and dreams, but it is also a reminder that we are not helpless, that we have the tools, the technology, and the knowledge to see these threats coming. And if we act wisely, we have the capability to do something about them. So when 2024YR4 passes by in December 2032, and it almost certainly will pass by, it will not be the end of the story. It will be the beginning. A new chapter in humanity's ongoing effort to protect our planet from the dangers lurking in the cosmos. Understanding the threat level of an asteroid requires more than just knowing its size and speed. It requires a standardized system that can communicate risk in a way that scientists, governments, and the public can all understand. That system is called the Torino scale. And in January 2025, 2024YR4 became one of only a handful of asteroids in history to reach level 3 on that scale. To understand what that means, we need to take a step back and look at how the Torino scale actually works. Developed in 1999 by Professor Richard Binzel at the Massachusetts Institute of Technology, the Torino scale is a color-coded system that rates asteroid threats on a scale from 0 to 10. 0 means no hazard. The asteroid will either miss Earth entirely or burn up harmlessly in the atmosphere. 10 means certain collision with global catastrophic consequences. Think extinction-level event. Everything in between represents varying degrees of concern. The scale is divided into 5 color zones: white, green, yellow, orange, and red. White and green represent minimal or no threat. Yellow means the situation deserves careful monitoring. Orange indicates a serious threat that warrants government attention and contingency planning. Red means a collision is certain and catastrophic damage is inevitable. 2024YR4 sits firmly in the yellow zone at level 3, and that is significant. To put it in perspective, the vast majority of asteroids discovered each year never make it past level 0. Even level 1 is rare. Most objects either pose no threat at all or have such low impact probabilities that they barely register. Level 2 asteroids deserve attention from astronomers, but are still considered unlikely to hit. Level 3 is where things start to get serious. It is defined as a close encounter with a localized destruction potential. The probability of collision is still low, typically around 1% or slightly higher, but high enough to warrant public awareness and continuous monitoring. In other words, level 3 does not mean panic. It does not mean start building bunkers or stockpiling supplies. It means keep an eye on it. It means scientists need to gather more data, refine the orbit calculations, and prepare contingency plans just in case. So why did 2024YR4 reach level 3? 2 main factors. First, its impact probability peaked at just over 3% in mid-February 2025. That might sound small, But in the world of asteroid tracking, 3% is alarmingly high. For comparison, most near-Earth objects have impact probabilities measured in fractions of a percent or even fractions of a fraction. A 3% chance of hitting a major population center is something planetary defense agencies take very seriously. Second, the potential damage is significant. As we discussed earlier, 2024YR4 carries enough kinetic energy to release approximately 8 megatons of TNT upon impact. That is not a global killer, but it is absolutely a regional catastrophe. If it hit a city, the death toll could reach hundreds of thousands or even millions, depending on the location and population density. Those two factors combined, moderate probability and significant potential damage, push 2024YR4 into level 3 territory. But here is the crucial thing to understand. The Torino scale is not static. It changes as new data comes in. Every telescope observation, every radar measurement, every orbital calculation adjusts the risk assessment. And for 2024YR4, that is exactly what happened. As astronomers continued tracking the asteroid throughout early 2025, the impact probability began to drop. More data meant more precise orbital calculations. More precise calculations meant narrower uncertainty margins. And narrower margins meant fewer possible impact scenarios. By late February, the probability had fallen below 1%. By spring, it had dropped even further, and with each passing month, the likelihood of impact continued to shrink. If current trends continue, 2024YR4 will eventually drop back down to level 0 or level 1, joining the thousands of other asteroids that were briefly concerning but ultimately harmless. But even if that happens, the fact that it reached level 3 at all is historically significant. In the entire history of asteroid tracking, only a handful of objects have ever been rated level 3 or higher. The most famous example is Apophis, a 370-meter asteroid that briefly reached level 4 in 2004, before additional observations ruled out any near-term impact threat. 2024YR4 is smaller than Apophis, but it reached a similar level of concern due to the initial uncertainty in its orbit. The Torino scale serves another important function beyond just communicating risk. It helps prioritize resources. Planetary defense agencies around the world have limited budgets, limited telescope time, and limited personnel. They cannot monitor every single asteroid with equal intensity. The Torino scale helps them decide where to focus their efforts. A level 0 asteroid gets minimal attention. A level 3 asteroid gets round-the-clock monitoring, international coordination, and serious consideration of deflection options if the risk continues to rise. In the case of 2024YR4, reaching level 3 triggered a massive international observation campaign. Telescopes in Hawaii, Chile, Spain, Arizona, and South Africa all turned their instruments toward the asteroid. Space-based observatories, including the James Webb Space Telescope, captured infrared images to determine the asteroid's size and composition. Radar facilities in California and Puerto Rico pinged the asteroid to measure its distance and velocity with incredible precision. All of that data fed into sophisticated computer models that simulated thousands of possible trajectories. Scientists ran Monte Carlo simulations, generating millions of virtual asteroid orbits based on the observational uncertainties. They calculated the line of variations, a mathematical technique that identifies the most likely path through the uncertainty space. They analysed every possible scenario, from direct hits to near misses, and assigned probabilities to each one. And slowly, methodically, the picture became clearer. But here is where the Torino scale reveals its limitations. It is excellent at communicating the current level of risk, but it cannot predict the future. An asteroid at level 3 today could be level 0 tomorrow if new observations rule out impact. Conversely, an asteroid at level 1 could jump to level 8 if new data reveals a previously undetected collision course. The scale is a snapshot, not a forecast. That is why continuous monitoring is so critical. Asteroids do not sit still. Their orbits change, sometimes subtly, sometimes dramatically. Close encounters with planets can alter their trajectories. Solar radiation can create tiny but cumulative forces that push them off course. Even the simple act of spinning through space can generate asymmetric heat radiation that changes their orbit over time, a phenomenon called the Yarkovsky effect. For 2024YR4, every observation adds clarity. Every data point shrinks the uncertainty cone. And every passing week brings us closer to knowing, with absolute certainty, whether this asteroid will hit or miss. If the probability drops to effectively 0, the Torino scale rating will be downgraded, and the asteroid will fade from public consciousness. But if the probability rises, if new observations reveal a tighter trajectory that increases the likelihood of impact, the rating could climb to level 4 or even higher. Level 4 means a close encounter with a 1% or greater chance of regional devastation. Level 5 means a significant threat requiring contingency planning. Level 6 and 7 means certain impacts with regional to global consequences. And levels 8, 9 and 10 mean catastrophic collisions that could threaten civilization itself. Right now, 2024YR4 sits at level 3. Not dangerous enough to justify immediate action, but concerning enough to demand serious attention. It is a reminder that the universe is not empty. That space is filled with rocks, some small, some large, all moving at incredible speeds. And every so often, one of those rocks crosses paths with Earth. The Torino scale exists to help us make sense of that chaos, to transform raw orbital data into something meaningful, to give us a framework for understanding risk and making informed decisions. 2024YR4 is a perfect example of the system in action. It was discovered, assessed, rated, and monitored. Scientists communicated the risk clearly, governments paid attention, and the public, for the most part, remained calm but informed. That is exactly how the system is supposed to work. No panic, no hysteria, just careful, methodical science. But level 3 also serves as a warning. It tells us that we are not immune, that even in the 21st century, with all our technology and knowledge, we are still vulnerable to threats from space. It tells us that detection is only the first step. Monitoring is the second, and if necessary, deflection will be the third. The Torino scale does not just measure risk, it measures preparedness. And in the case of 2024YR4, it is forcing humanity to ask a critical question. If this asteroid were on a definite collision course, what would we do about it? That question brings us to the next chapter of this story. Because for the first time in human history, we actually have an answer. That question brings us to the final chapter of this story. Because for the first time in human history, we actually have an answer. We are not defenseless, and 2024YR4 might be the asteroid that proves it. As we approach December 2032, astronomers continue tracking this space rock with unprecedented precision. Every new observation brings us closer to the final answer. Will it hit or will it miss? But more importantly, this asteroid has triggered something bigger than just scientific curiosity. It has forced governments around the world to take planetary defense seriously. In the months following the discovery of 2024YR4, something remarkable happened. Countries that had never discussed asteroid threats before suddenly established planetary defense offices. China announced the creation of a dedicated near-Earth object monitoring program specifically in response to this event. The European Space Agency expanded its space safety program, allocating additional resources to asteroid tracking and deflection research. NASA increased funding for its Planetary Defense Coordination Office and accelerated plans for future missions, all because of one 50-meter space rock. But this response was not just about 2024YR4, it was about preparing for the next one. Because as we have learned, asteroids are not a one-time problem. They are an ongoing threat that requires constant vigilance. The good news is that we have already tested our planetary defense capabilities, and the results were spectacular. On September 26, 2022, NASA deliberately crashed a spacecraft into an asteroid called Dimorphos. The mission, called the Double Asteroid Redirection Test, or DART, was humanity's first attempt to change the trajectory of a celestial object. The target was a small moon orbiting a larger asteroid named Didymos. Neither posed any threat to Earth. They were simply test subjects. The DART spacecraft, about the size of a small car, slammed into Dimorphos at over 22,000 kilometers per hour. The impact was not designed to destroy the asteroid. That would be impossible and counterproductive. Instead, it was designed to nudge it, to change its velocity by just a tiny amount. And it worked. Spectacularly. Before the impact, Dimorphos took 11 hours and 55 minutes to orbit Didymos. After the impact, that orbital period changed by 32 minutes. 32 minutes might not sound like much, but in the world of orbital mechanics, it is enormous. It proved that kinetic impact, the technique of simply ramming a spacecraft into an asteroid, can successfully alter its trajectory. If we can change the orbit of Dimorphos, we can change the orbit of 2024YR4, or any other asteroid that threatens us. But here is the catch. Deflection requires time, lots of time. The DART mission worked because we had years to plan it, build the spacecraft, and execute the impact. If we only had months of warning or weeks, the options would be far more limited. That is why early detection is so critical. And that is why 2024YR4, despite its low current impact probability, is so valuable. It gives us 7 years. 7 years to watch, to plan, and if necessary to act. So what would happen if the probability suddenly spiked? If new observations revealed that 2024YR4 was definitely going to hit Earth? The response would unfold in stages. First, verification. Multiple observatories would confirm the trajectory independently. No single telescope or calculation would be trusted. The stakes are too high for errors. Once confirmed, space agencies would convene an international coordination meeting. NASA, the European Space Agency, the China National Space Administration, Roscosmos, and other major players would assess the threat and determine the best course of action. The most likely option would be a kinetic impactor mission similar to DART. A spacecraft would be designed, built, and launched to intercept 2024YR4 several years before its predicted Earth impact. The spacecraft would not need to be large, just heavy enough and fast enough to deliver a meaningful change in velocity. The earlier the impact occurs, the smaller the required change. A nudge applied 5 years before impact could deflect the asteroid by hundreds of thousands of kilometers. The same nudge applied 6 months before impact might only shift it by a few thousand kilometers. Timing is everything, but kinetic impact is not the only option. Scientists have explored numerous asteroid deflection techniques, each with its own advantages and drawbacks. One alternative is the gravity tractor. This involves parking a spacecraft near the asteroid for months or years. The spacecraft's gravitational pull, tiny but persistent, would gradually tug the asteroid off course. This method is slow but precise. It requires no explosive impact, no complex maneuvering, just patience. Another option, more controversial, is nuclear deflection, not nuclear destruction, which would simply break the asteroid into multiple dangerous pieces, but nuclear deflection. A nuclear device detonated near the asteroid's surface would vaporize a portion of the rock, creating a jet of material that acts like a rocket engine, pushing the asteroid in the opposite direction. This technique is powerful and fast, but it carries political and technical risks. No nation wants to launch nuclear weapons into space, even for peaceful purposes, without international consensus. For 2024YR4, given its relatively small size and the amount of warning time, a kinetic impactor would almost certainly be the preferred method. Simple, proven, and effective. But regardless of the technique, the key is early action. The longer we wait, the harder deflection becomes. And that brings us back to the present moment. Where do we stand right now? As of late 2025, 2024YR4 has been downgraded significantly. Additional observations throughout early 2025 continuously refined its trajectory. By late February, the asteroid was reduced to a Torino scale rating of 0. By early April, NASA officially removed the chance of a 2032 Earth impact. The European Space Agency made the same determination in early March. In other words, Earth is safe. 2024YR4 will not hit us in 2032. But the story does not end there, because while the threat to Earth has been eliminated, a new possibility has emerged: the Moon. Recent calculations suggest that 2024YR4 has approximately a 4% chance of impacting the Moon on December 22nd, 2032. That probability is based on updated size estimates from the James Webb Space Telescope, which observed the asteroid in infrared wavelengths and determined it is approximately 53 to 67 meters in diameter. Slightly smaller than initial estimates, but still large enough to create a significant lunar crater if it hits. A lunar impact would not threaten Earth directly. The Moon is far enough away that debris from the impact would not rain down on us, but it would have consequences. First, it would create a spectacular show. The impact would be visible from Earth, potentially with the naked eye, depending on the time of day and viewing conditions. Observatories around the world would capture the event in stunning detail. Second, it would pose risk to lunar missions. Several countries, including the United States, China, India, and private companies, have plans for lunar exploration in the coming years. Habitats, rovers and scientific instruments on the moon could be damaged by the impact or by ejected debris. Third, it would provide an unprecedented scientific opportunity. Studying the impact would reveal details about the moon's subsurface composition, the mechanics of crater formation, and the behavior of asteroids during high-speed collisions. It would be a natural experiment on a scale we could never replicate artificially. But a 4% chance is still a 96% chance of missing, and that probability will continue to evolve as we gather more data. The asteroid will pass close to Earth again in 2028, approximately 20.8 times the Earth-Moon distance, or about 8 million kilometers away. That flyby will provide another opportunity for detailed observations. Radar measurements, optical tracking, and possibly even spacecraft reconnaissance could nail down the trajectory with extreme precision. By late 2028, we will know with near certainty whether 2024YR4 will hit the moon or sail past it harmlessly. Until then, astronomers will keep watching, not with alarm but with professional interest, because 2024YR4 has already served its purpose. It has demonstrated that our detection systems work, that international coordination is possible, that we can track potentially hazardous objects years in advance and calculate their trajectories with incredible accuracy. And perhaps, most importantly, it has proven that planetary defense is not science fiction, it is science fact. We have the tools, we have the knowledge. And thanks to missions like DART, we have the capability to deflect asteroids if necessary. 2024YR4 may not be the asteroid that forces us to use those capabilities, but it has forced us to prepare. It has sparked conversations in government offices, research labs, and international forums. It has reminded humanity that we share this solar system with countless other objects, some of which pose real dangers, and it has demonstrated that with vigilance, cooperation, and advanced technology, we can protect ourselves. The universe is vast, chaotic, and indifferent to our existence, but we are not helpless passengers on a fragile planet. We are active participants in our own survival. And 2024YR4, whether it hits the moon, misses entirely, or simply fades into the background noise of near-Earth objects, will be remembered as a turning point. The asteroid that made planetary defense real. The asteroid that turned hypothetical scenarios into concrete plans. The asteroid that reminded us to look up, pay attention, and take the cosmos seriously. Because the next one is coming. Maybe not today, maybe not tomorrow, but eventually another asteroid will appear on our telescopes with a trajectory that threatens Earth. And when that happens, we will be ready. Not because we got lucky, but because 2024YR4 taught us to prepare. That is the real legacy of this 50-meter space rock. Not destruction, not fear, but preparedness. A wake-up call that humanity answered with science, cooperation, and determination. The countdown to December 2032 continues. The world watches, and whatever happens, we will face it with our eyes open and our defenses ready, because for the first time in human history, we are no longer defenseless against the dangers lurking in the void. We are guardians of our own planet, and that changes everything.